In March 2023, a single ChatGPT query began consuming more electricity than a Google search. By the end of that year, OpenAI was projected to burn through more power than some European nations. The entire artificial intelligence industry had crossed into physical reality. Microsoft signed a 20-year power purchase agreement to restart 3 Mile Island. Amazon acquired a nuclear-powered data center in Pennsylvania for $650 million. Google began negotiating with reactor developers to secure dedicated gigawatt-scale generation. These were not sustainability gestures. They were survival mechanisms. The digital economy had run into a wall made of physics. This is Solidus, where history and money collide. For 2 decades, the internet operated on an elegant deception. Cloud computing was marketed as weightless infrastructure. Data was abstract. Processing was invisible. The entire system appeared to float above material constraints. This was never true. Every query, every transaction, every model inference required electricity, but the scale was manageable. A Google search consumed 0.3 watt-hours. A Netflix stream required steady but predictable power. Data centers could be built near cheap hydroelectric dams or placed in regions with surplus wind generation. The grid absorbed the load without restructuring. Artificial intelligence changed the math. A single GPT-4 query consumes roughly 10 times the energy of a traditional search. Training a large language model requires the equivalent electricity output of a small city running for weeks. Inference at scale, deploying these models to billions of users, demands continuous, uninterrupted power at levels the renewable grid was never designed to provide. The bottleneck is not computational, it is thermodynamic. Hyperscale AI infrastructure cannot tolerate downtime. Models must remain live, responsive, and globally distributed. Latency is measured in milliseconds. Availability is measured in uptime percentages that begin with 4 nines. Solar generation peaks midday and disappears at night. Wind power fluctuates with atmospheric pressure. Battery storage at the scale required to buffer a multi-gigawatt data center does not exist in deployable form. Lithium-ion arrays can smooth demand for hours, not days. AI requires baseload power. Constant, dense, geographically stable generation that operates regardless of weather, season, or time. Only 2 energy sources provide this at scale: fossil fuels and nuclear fission. Fossil infrastructure was already under coordinated regulatory and financial pressure. Carbon taxes, emissions caps, and investor divestment had begun dismantling coal plants across developed economies. Natural gas could fill gaps, but it remained politically vulnerable and geographically constrained by pipeline access. Nuclear energy had spent 40 years in regulatory stasis. After 3 Mile Island, Chernobyl, and Fukushima, construction had nearly ceased in the West. Existing plants aged into decommissioning windows. The uranium fuel cycle remained operational, but no new reactors were being built at the pace required to replace retiring capacity. Then the AI boom made nuclear the only option left. The shift was not ideological, it was financial. Tech companies do not build power plants because they care about carbon neutrality. They build them because curtailment risk threatens quarterly earnings. If a data center loses power for 30 seconds, millions of dollars in compute contracts evaporate. If a model training run is interrupted, weeks of GPU time are lost. Renewable energy could not guarantee this. Power purchase agreements with wind and solar farms included clauses for generation variance. Utilities could not promise uninterrupted supply from intermittent sources. Nuclear plants operate at 90% capacity factors. They run continuously for 18 months between refueling. They generate power in geographic proximity to demand, eliminating transmission losses. Most importantly, their output is not weather dependent. The economics became obvious. Microsoft did not restart 3 Mile Island for public relations. It did so because Pennsylvania sits near existing fiber infrastructure and offers direct access to a reactor capable of producing 835 megawatts without new construction. The capital cost was lower than building equivalent solar capacity with battery backup. Amazon's acquisition of the Cumulus data center was even more direct. The facility was co-located with the Susquehanna nuclear plant. Power was delivered on-site with zero grid dependency. Amazon paid a premium for something no renewable installation could provide: elimination of supply chain risk. Google's negotiations with reactor developers were not about decarbonization. They were about locking in long-term power contracts at predictable costs before competitors could do the same. This was not a technology transition. It was a resource capture event. Nuclear fuel is abundant but controlled. Uranium mining is geographically concentrated in Kazakhstan, Canada, and Australia. Enrichment capacity is even narrower, with significant processing infrastructure in Russia and China. Reactor construction requires specialized labor, regulatory approval, and decade-long timelines. The companies that secure nuclear power early gain a structural moat. Competitors who arrive late face either higher costs or power shortages that throttle model deployment. The digital layer began to fossilize into physical infrastructure. Governments had spent decades trying to decommission nuclear plants. Regulatory agencies treated fission as a liability to be managed down toward zero. Waste disposal remained unsolved. Public opinion was hostile, but public opinion does not override industrial demand at scale. When Microsoft announced 3 Mile Island's restart, federal regulators approved the plan in under 6 months. When Amazon moved to co-locate data centers with reactors, state-level permitting that normally required years of environmental review was expedited. The system had reoriented. Nuclear energy was no longer being evaluated as a societal good. It was being evaluated as critical infrastructure for maintaining the compute layer that now underpinned financial markets, logistics networks, and state surveillance apparatus. The same governments that had restricted reactor construction began fast-tracking approvals. The failure was not technical. Renewable energy works. Solar and wind are cheaper per kilowatt hour than nuclear in most markets. Battery costs have fallen exponentially. Grid-scale storage is improving. But AI does not care about cost per kilowatt hour. It cares about cost per uninterrupted kilowatt hour at the required scale and location. Renewables could not provide this. Nuclear could. The rhetoric of sustainability had always been secondary to the logic of procurement. The revival of nuclear energy is not a policy decision. It is a survival response to a system that can no longer function on intermittent power. The global economy is now dependent on AI tools that require generation densities incompatible with renewable timelines. This was predictable. The moment intelligence became a commodity sold at API endpoints, it became subject to the same material constraints as oil, steel, and semiconductors. The digital age did not escape scarcity. It just delayed the confrontation. Now the confrontation is here. The companies that control the models will control the reactors. The countries that permit the plants will host the infrastructure. The ones that do not will import inference as a service from those that do. Power has always been about endurance. The system that lasts is the one that secures the energy to keep running when others go dark.